Okay, I'll just introduce myself first. I'm Delphine. I don't like being called a technical project manager or team lead. My job description is actually to make things happen, and that's the title of the speech this morning. And maybe problem solving? Yeah, good. That's brilliant. So my background, I'm actually an electrical and electronic engineer. I'm a proper, sorry Susan, a proper tech person. I've had the opportunity of actually doing an engineering school in France, and that's where I started. And through that engineering course, we learned a lot about, how to get things done, have a kind of a recipe to go from nothing to actually getting a solution. And that's what I'm going to try and share with you this morning. So, first, in the recipe, it's believe. I've been lucky enough, my parents have always told me since I was little, you can do anything you want, and they made me believe that. And today I believe that everything is possible. So I don't like to hear anybody saying, oh no, that's impossible. I've heard that so many times, and through hard work and dedication and, a little bit of luck as well, you can make things happen. It's not impossible. Everything is possible, with a little bit of caveat that, you need some time and some resources to be able to achieve things. But most importantly, and we discussed that yesterday during the panel, you need to believe in yourself, because if you don't think that you're going to make something happen, if you don't believe in yourself, then who else is going to do that? Who else is going to believe in you? Who else is going to give you a chance to actually achieve things? So that's super important. That's the first really insight that I wanted to share with you. The second thing is a little bit of a process. And the first step in that process is that identifying a goal. Now, whether you've got a project to run or whether you're organizing a meal, it's always the same thing, right? You've got to identify what you're aiming for. What is going to be the end result? Because if you're planning a meal for two and then you've got 40 friends coming along, it's going to be quite difficult. So identifying the goal, knowing what you're aiming for, having a vision of what's going to happen is primordial to success. Second thing, research. We've heard that also throughout the couple of days. You need to do your research. You guys have got access to internet, so much information that you've got your hands on. Do it and do it properly. There's no point in, going down the rabbit hole, because you could waste a lot of time looking at things that are not relevant. Do some proper research. Then once you've done your research and you've come up with potential solutions, you need to evaluate every solution, because you might have constraints with your project. Whether it's cost, whether it's time, whether it's resources. You might have all sorts of things that you need to take into account, and that will lead you to the choice of the right solution. If you've got something that you just need to run a proof of concept, you're not going to go to a solution that requires months and months of work. You want something quick and dirty, just to prove that something can happen. But obviously, when you go to the public with it, with your solution, and you want to make that a product that people are going to use day in, day out, and be able to scale up, then you're going to need to look at a different solution where, you've got to iron out a lot of the issues that your proof of concept might have brought up. Planning. I'm sure as students you do that too when you've got work assignments. Hopefully you do anyway. So having the solution, then you plan. You never go from A to Z in one go. Plan carefully, know what you're going to do, what is the next step, and then the step after that, and then the step after that. Because sometimes when you go down and you start working, you might actually, forget about everything, and then you lift up your head and you look, so where is my aim again? And you've gone completely in the wrong direction. So plan carefully. It's useful for time, it's useful for work. Then the exciting bit, at least for me, it's to execute, is actually to go and do it, make it happen. And once you've made it happen, the last thing is you refine, because no work is fully complete. You can always improve. And there you go, going round and round again. Process is great, but you also need some other skills, right? Because everybody can follow a process, but other things that you need to do, you need to be innovative. You need to work smarter and harder. I know that's a bit of a cliche, but it is true, right? You need, I was saying in your research, you need to do that research in a smart way so that you're actually going and zooming in on the solution that's going to make it happen. You might have solutions that exist out there. I mean, who hasn't used Google or to actually find a solution to a problem? A teacher asked you to answer a question, and the first thing you do is you go and Google it. It's the same. You might have a problem, and somewhere out there, even if you don't have 100% of a solution, you might have maybe 50, and then if you find something else, that you will get another 30%. And you've got to be innovative in actually putting those bits together. And maybe some of the things that you find are not meant to solve the problem you have, because they've been developed for a different area, it's different technology that is not meant for you. So something in medicine, why would you use that in oil and gas, or vice versa? But if you think about it, things might actually make sense. Communication and teamwork, I know sometimes it feels like it's difficult to do, but no communication, no teamwork, and you're not going to go anywhere. Things on your own, you're not going to progress as fast as you would if you were talking to other people. That's why you've got all those blogs, right? That's why you've got all these sites where you can actually ask your questions and get other people to answer, or actually give you some insight about what they've done. That's also called teamwork. Never work on your own, and especially do not be afraid to fail. Failure is a part of learning, right? Now, it's all kind of theory and stuff, and I want to show you what we did in about 15 years in the oil and gas industry, how we took the technology and through innovation, using other bits of technology from other places, how we actually made the oil and gas exploration evolve over time. Starting point about 25 years ago, anybody thought or gave a thought ever about how oil and gas companies are actually trying to find petrol when it's buried, 2-3 kilometers under the surface? No, I guess not. Well, they do seismic imaging, and what that does is that they send a big sound wave down in the ground, and they've got a series of microphones, and the sound waves is going to bounce off all sorts of things, different types of rocks and things like that. And you're going to get some signal back. And they've got an array of microphones, and they're picking up the signal that's coming back up. And 25 years ago, they were doing that in some weird ways, or not weird ways. That was the norm at the time. So you had just lines of microphones, and they would just send that signal and get, the return on that particular line. And they had to do that again and again, so they would crisscross the area that they were interested in. And the result of that is something that looks like that. Now, personally, when I started working in that field, that didn't mean anything to me either. But then, when you look at a picture of what you can see from the surface, right? You can see the stratas of the different rocks, and basically what you get is pretty much the same, except that it's buried quite deep down. Now, this is not user-friendly to interpret. I don't think, anybody can say the contrary. And so the guys thought, okay, how can we make it better, faster, and more accurate to interpret subsurface data? And one of the first things they thought about was capturing 3D images, right? So cubes of data instead of just lines, so that you would have information in all directions. Because after all, you're not going to shoot, or your line of microphones is not going to be exactly parallel or perpendicular to a feature that you're looking at. So having 3D images or 3D arrays of microphones changed the resolution and the content, the information content of the data. So left here you've got your 2D, and right, it's once you've done a 3D survey, you can see that you get a lot more information. But then, having all that data, what are you going to do with it? Okay, remember, we're talking about 25 years ago. Yesterday we had a speaker saying she had that computer with 640K of RAM. Well, 25 years ago it wasn't much better, right? You needed to actually work on Unix stations with, I think I had 16 megs of RAM when I started, and 2 gigs of hard disk. That was pretty cool. That was a big machine at the time. And those 3D images, or the volume of data you're getting, are actually megabytes. Now they're actually gigabytes, and even some are terabytes of data. So how do you process, or how do you image, or what do you do with 3D volumes of data that are so big that they actually barely fit on your computer? So in order to make sense of those 3D images, we developed many things, and we took from different areas, different technologies. So 3D image processing, we developed a library of image processing functions that could actually work in 3D. And we picked them from everywhere. So most of the time, I was given a paper, a publication that had been put in whichever journal. It was usually for a 2D image processing routine, and we had to be, innovative and try and make it work in 3D. Then once you've done that, once you've made your image a little bit better, then you want to visualize it. And then obviously interpret it, because that's the name of the game in oil and gas. You need to find out where your oil reservoirs are and how you're going to drill. So there are some pictures here. This is actually 3D visualization of a seismic block of data. And you can still cut through your 2D slices as you're used to, but what's important is also to look at the data in 3D, because, as I said, things are not necessarily going across or along the volume of data. And visualization is obviously key to what you're doing. 3D interpretation, that's real. I'm not expecting that to make sense to anybody, but in there you've got a lot of information, and actually you've got, in the bottom in orange there, you do have, I'm not sure if there's a pointer on there. Yeah, no, you can't see. But there's a reservoir down there, and they've mapped it through all sorts of different things. But that means a lot to geologists and geoscientists in the oil and gas industry. And they also were the first people, I think, who used virtual reality and applied it to an industry. And what happened there, obviously we can't see it because they've got the goggles and we don't. But these guys are actually walking through their data. I've seen people looking at, walking through their data and then looking around a particular feature to see what happened behind. That was pretty cool. Now, as I said, loads of data, it requires a lot of computing power. And dealing with gigabytes of data, some routines, some image processing routines, you could have, take 24 hours or more to run through a volume. And one of the great things that we did eventually, when NVIDIA decided to release their CUDA API, so we could work directly on the graphic processing unit. Anybody knows NVIDIA? Not many gamers in the audience. But NVIDIA is a company that does graphics cards. They're the guys who allowed us to go from this to this in gaming, right? And what they've allowed us to do, because we could access the GPU and we could run our huge, image processing routines with all that data on the GPU directly, we cut down the time of processing from, say, 24 hours down to 2 hours, and sometimes down to minutes. So can you believe how much data you can go through when you've got that kind of processing power? And it was all on a PC. Pretty cool. And what that's allowed us to do, that's allowed us to explore our data in a whole new, different way. And that's the kind of images that we're getting. I'm not going to tell you what the processing was like to get to that thing. But when I saw that picture the first time, I thought, wow, that's pretty cool. Anybody can tell me what that weird shape here on the left is? Anybody can give me a guess? Chiara, no, you're not allowed. No? No one? No guess. Come on, be brave. No. All right, okay. Well, that thing is actually about 6 kilometers across, so it's not a giant snake. It's about 3 kilometers deep under the subsurface, on the surface rather. And this is a prehistoric river. Now, why it shows differently in the image is just because, over time, the river got filled up with sediments and with pressure and all the rest of it that made it different to the rest. And using some image processing techniques, we can actually visualize clearly stuff that's, 3 kilometers beneath the surface. I mean, that's pretty cool, I think. So not only I was an engineer and a software developer and all that, but suddenly I became an explorer. And I really like that bit. And another thing that we discovered, but not in the same area, is actually in the North Sea. Okay, we're back to our 2D line of data. And this actually comes from British Petroleum. They were looking at some data in the North Sea, and they saw some weird thing happening not far below the surface. You see that blue line and those funny red lines going towards the center there, and that was a very, very odd pattern. And they were wondering, what could that be? So we worked with them on processing the data, and we came up with a 3D view of that blue line there. And And it was quite interesting, right? A big center, quite deep down, and then some rings around, fractures. So again, anybody can have a guess about what that is? Sorry? Almost a volcano. A crater, yes, it's what is believed to be a meteorite crater, the only one in the UK. And that was discovered by chance when they were actually looking at drilling in that area. So just to let you know, it's about 40 to 60 meters deep under sediments, and then there's another 300 meters of water on top of that. Now, I like that picture, and the thing is that it's awfully similar to this. But that's not on Earth. That's actually on Europa, one of Jupiter's moon. And you can see the similarity between the two images, right? And that's definitely a meteorite crater. So it's quite cool. But engineering is not just about, making big companies make even more money or bigger profits. We use the same technology to look at the medical side of things, and we apply that to highlight brain tumors, obviously in the head, because that's where it is. But we were combining different types of scans, with one showing the soft tissue, that would show actually the tumor, and the other one the bone area, and combining the two, and then using the same technology that we use to highlight some of those oil reservoirs to highlight the tumor, and be able to place it exactly in the skull so that doctors could plan their treatment better. And that's what it is. Technology is not just about doing things in one area. Loads of things are emerging. We've talked about AI, we've talked about IoT and blockchain and everything. I think our role, and your role especially as the future generation, is to develop more of those new technology, make them work together, and make them work in a good way, right? Don't get pulled into the dark side. Use the tech for the good and the better good of everybody. I mean, blockchain, I know we talked about cryptocurrency, but it's so much more than that, right? It's helping with the overfishing of tuna, for example, or helping farmers in Africa get a better deal for their produce. So it's not just about money, right? Let's not forget that. There's so much more. So that's just to finish. On that note, I wanted to, I don't know if you guys know that comedy, which is The Big Bang Theory. And I wanted to give them the last word. Maybe? Whoops. No, it's not working. Come on. Can you play the video? Yes.
Thank you to the Nobel Committee. We are deeply honored. I would just like to take this moment to say to all the young girls out there who dream about science as a profession, go for it. It is the greatest job in the world. And if anybody tells you you can't, don't listen. And now, speaking of not listening, my husband, Dr. Sheldon Cooper. Sheldon.
Well, did you finish? Great job.
All right, thank you very much for listening.